assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
In this example, we have a circuit here that's broken up into this square loop, this rectangular loop, and also a little semicircle that juts out from the rectangular loop. And this semicircle is attached to this crank so that we can actually spin it around such that it could flip around to the other side like this. And what we want to know is if we do that, so if we crank it through one half rotation at 180 degrees, we want to know what the change in our total magnetic flux would be through this circuit. So remember, the magnetic flux through this loop is just going to be defined as B times A times the cosine of the angle between the magnetic field and the surface normal of our loop. In our case, the surface normal of our loop and the magnetic field are parallel. So the cosine of theta is the cosine of 0, which is just 1. So now all we have to figure out is what our total flux is going to be. And you can imagine if we broke up our circuit here into the rectangular part and the half circle part, we could say that the total flux was the contribution of flux from the rectangle plus the contribution of the flux from the half circle, which in this case is just going to be B times A, where A is the area of our half circle. So the area of a circle is just pi r squared. So the area of a half circle is just pi r squared over 2. So we should have pi r squared over 2 here. Okay. Now, when this loop flips over, we can see that the surface normal is actually going to be pointing in the opposite direction, right? Before we said the surface normal for this loop was going to be pointing into the page, just like the magnetic field, but now it's going to be pointing out of the page. Or we can express that with our flux equation here. So this was flux initial. We could say that the final flux is going to be the contribution from the rectangular part of our circuit, which is the same as the first part. But now our loop makes an angle of 180 degrees with the original surface normal because we flipped it around 180 degrees. So this would be B times A times the cosine of 180, which the cosine of 180 is -1. And again, the area is just 1/2 pi r squared. So we'd end up with big phi of the rectangle minus B pi r squared over 2. Now, if we look at the change in the flux here, we'll just take the final flux minus the original. So we can see if we subtract flux final from flux initial, they both have a rectangular contribution to them here. So those will just cancel each other out. And then from the final contribution, we'll have a minus B pi r squared over 2 minus the exact same thing except positive. So B pi r squared over 2. Or since those are the exact same term there, we'll just have 2 times that. So we'll have 2 times B pi r squared over 2, which is just minus B pi r squared. So here is the total change in flux, which makes sense that it's negative because we are going from having a bigger area to a smaller area when the loop flips around, right? So if we calculate that, we should get that our change in flux is equal to minus 0.094 Webers, or Tesla's meters squared, either one.